And the situations we normally are going to encounter are going to apply to some sort of objective function. And maybe the objective function is I, that stands for something, I don't know, interest or something like that, depending on the word problem that it comes from. And they'll usually give you the objective function. And what we have to do with the objective function is maximize or minimize. We'll do one, or we're going to do both for this problem, but usually the question you're given will tell you to do one or the other, not both. Maximize for or minimize for the given constraints. Constraints are inequalities that we have to graph and find the solution area for. All right, so many times with inequalities, you will have x is greater than or equal to 0, y is greater than or equal to 0. Most of the time, with word problems, that's going to be the case because you're dealing with real world problems, and unless we're dealing with money, it rarely goes into negatives with that, because if we're dealing with production or something like that, we want to deal with, okay, if we're making things, we're not losing things, that sort of thing. So those are pretty common as far as that goes. And then you might have some others that are specific to the particular problem, that the sum of the two things is less than or equal to 25, or is at most 25. So you think about these things, we're going to try to talk about them in terms of, if you see things in a word problem, you're going to have some that are just straight up giving you the constraints already, but you're going to see some word problems that you've got to pull those out of as well. So it just takes a little bit of thinking on that part. But most of those things are coming from keywords like at most, less than or equal to. At least would be greater than or equal to, as far as the words that go along with these constraints that go with that. And then x is greater than or equal to 15, y is less than or equal to 5. Okay, so the key to this is graphing all of those constraints on the same coordinate plane. And everything there looks like it's going to be a positive, so I'm going to draw my coordinate plane with mostly just first quadrant. And I'm going to scale my graph by 5. So I'm going to make each, let's do by 2.5, so it'll look a little better. So by 2.5, and this is going to be by 2.5 instead of 1. So each block counts as 2.5 out of that. So that kind of makes my picture a little bit better. So when you're dealing with word problems, especially, sometimes they'll be dealing with things in thousands, so you might want to go by hundreds or something on your scale. Just change your scale so that you can see what's going on there. So x is greater than or equal to 0. That'd be just that vertical line, and we know our shading goes in this direction. I've got 1, 2, 3, 4, 5 constraints to do here. So I'm not going to shade all of them. I'm just going to put arrows on the line saying what direction the shading goes. And then hopefully at the end, I will have all the arrows pointing to one little area, and I'm just going to shade that one area, the solution area. Because if I tried to shade all 5 of these on here, you might could do it with your pencil, because you can draw lightly. I can't. It's either on or off. So I'm just going to use arrows to do that. And then the y is greater than or equal to 0. That'll just be the x-axis and going up from there. And then x plus y is less than or equal to 25. So I'm looking at that and thinking, okay, x-intercept would be 25, the y-intercept would be 25. That's one way to graph that. You could also get it in slope-intercept form to graph it. That's absolutely okay to do that. Same result. So to get to 25 on the x-axis and the y-axis, and my scale is 2.5, how many blocks do I need to go? 10. Okay, so that's the idea here. 1, 2, 3, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Drawing it. It's a solid line because it has the equal to mark. Pay attention to your constraints. If they don't have the equal to mark, then got to do the dashed line, the dotted line out of that. And then we have these two. Maybe that's just saying, okay, you have to make 15 of this particular thing, and you can't make more than 5 of these. Maybe that's what the word problem says. So that's where these may be coming from. So x is greater than or equal to 15, so that would be a vertical line. So I'd go to 15 would be 5, 10, 15. That'd be right there. Vertical line there. I need to do my shading on that green line before I forget it. X plus y is less than or equal to 25. If I tried 0, 0 in that, is 0 plus 0 less than 25? Yes. So the shading for the green line is going toward the origin there. So right before I put the shading for the purple line in, the solution area is this triangle here. Well, the purple one says x is greater than 15, so that's going to put the shading this direction for that one. So that's going to make that triangle even smaller. So right now, before I do the last one, I've got this triangle right here is the solution area. Now, when I add this one in, y is less than or equal to 5. So I'd go to 5. And there's that line. Less than would be down. So the solution area is this trapezoid shape here. That's the solution area for that set of constraints. Now, that means any points inside of that are solutions to all of these at the same time. But when we're trying to maximize or minimize a objective function, we need to look at the corners of our polygon that we make there. So that's what you're looking for, is that polygon shape that you're going to get. We need the corners to that. Okay, so we need to find the ordered pairs that are the corners to that. So what's that? These places here, those 4 ordered pairs are what we need. So this line, the orange line and the purple line connect at the point 15, 5, right? And then the orange line and the green line are going to be at something 5. Is it 25? 20. Okay, I got you there. Good. 25. How'd you find that?
Mine scaled to 5s.
You scaled to 5s? Absolutely works fine to do it that way. How would we find it since I scaled by 2.5s?
That means that every block is, like in the grid, it's halves or 2.5, so it just.
Yeah, okay. My graph is pretty precise. But how do I know that that's not like 0.48 and not, instead of halfway? So that's perfectly 20. I know y is 5 because I know where that line's at, right? So I can plug that back in here, and that's all those things that happen with systems of equations. If we have a more complex graph that's in between points, even no matter what scale we use, I want you to know that you can still do systems of equation things with these inequalities. Just treat them like equations because you're looking for where they're crossing. This is one of those things where if we're doing just systems of inequalities, we don't worry about ordered pairs. But if we're dealing with linear programming, we need ordered pairs. So we want to think about them in terms of systems of equations. Where are they crossing? So don't forget all of those things that you can do with that. It's nicer, obviously, if your grid matches up and you scale the right way and it lands on a great spot and you can see it real well. But you still can find those things. We also need this one, which is fairly easy, 15, 0. And then this one would be, we know that point is 25, 0. So we have those 4 ordered pairs, and we want to test them in our objective function that we got up here at the beginning, okay? So what we're going to do is just plug those in as x and y in our objective function. It was I is equal to 0.02x plus 0.03y. And we're going to plug in those ordered pairs. So I got 15, 0, and I'm just writing them because those first because I can see them. And then 15, 5, and 25. Those 4 ordered pairs. The corners of the polygon. Okay. Happens to be a 4-sided polygon here. May, depending on your constraints, what kind of shape you end up with. But you're looking for the corners, and that's where your maximum or minimum is going to happen at. So we plug those in. And work those out. So y'all help me out with math here. I don't have to pull out the calculator. All right, so 15, 0, when I plug that in, I get what? 0.3. And when I plug in the 25, 0.5, and 15, 5, be 0.3 plus 0.15, which would be 0.45. Is that right? Okay. And then 20 times 0.2, 0.4, and then 0.15 would be 0.55. So which one is the maximum and which one's the minimum? Yeah, so 0.3 is your minimum. And there's your maximum. In the context of a word problem, that would tell us if we're trying to maximize something, say that objective function is a profit function, and we're trying to maximize profit. That's what you want to do in business, right? Then we would know that we need 20 of this and 5 of that to maximize our profit. That would be in the terms of a word problem. If we're trying to minimize cost, maybe that objective function is a cost function. You want to minimize cost. Then to minimize cost, this is the ordered pair that we need to use. X is going to represent something. Y is going to represent another something. It may be, if we're talking about profit, X may represent revenue and Y may represent cost. And they work together to get that. So you're building these things off of word problems, and all that is kind of what you're going to see. If you flip over in your textbook to that section, and we'll kind of talk about 1 or 2 together. We'll work them out completely, but just kind of talk our way through what you're doing. So page 927, where this is 927. The problems that you're going to be working on page 927, you got 9 through 17. Those are the ones that are just straight up. They give you the constraints, they give you the objective function, and you just do the work. That's all those are. But when you get to 19 through 30, let's do through 29. Those are the word problems that you can look at. So let's look at 19 real quick there and kind of get an idea of what's going on there. It says a manufacturer of skis produces 2 types, downhill and cross country. Use the following table to determine how many of each kind of ski should be produced to achieve a maximum profit. And to achieve a maximum profit, then they wanted to know what is that maximum profit, and then what would the maximum profit be if the time available for manufacturing is increased by 48 hours. Okay, so they're nice to us and they build this little chart which can help you if you'll try to maybe build that chart for the other word problems that they don't give you that for. It does make it easier when you've got that chart there. So when you've got the stuff going on there, you got downhill skis and cross country skis, and then you've got time available. So you've got a couple of different things going on there. You've got manufacturing time and finishing time for those. So for downhill skis, it takes 2 hours to manufacture and then 1 hour to make a cross country ski, but you only have 40 hours of manufacturing time available in a week. Right? So if you have to declare, okay, well, what's X and Y going to be? Well, I would say X should be downhill skis and Y should be cross country skis. That makes some sense. Maybe you want to use, different variables, but that it doesn't matter. So you could have a manufacturing inequality that manufacturing time inequality could be 2x plus 1y has got to be less than or equal to 40. Because you can't work, because your manufacturing time you have is 40 hours. We may not work, may not have 40 hours this week, so we could have less than that we're manufacturing, but 40 hours is the maximum amount we could have. So less than or equal to 40 would be that one. The second line there, the finishing time, we have 32 hours of finishing time that we can use. It takes 1 hour for downhills and 1 hour for cross country. What would the inequality be for that? X plus Y is less than or equal to 32, right? And you have two inequalities. We also know that we're going to manufacture skis. So we downhill skis, we're going to make more than zero, right? We're going to make more than zero cross country skis. So that's where you get the X is greater than or equal to 0 and Y is greater than or equal to 0. So what's going to happen there is when you draw those inequalities, you're going to find a polygon shape that's the solution area. And you find the corners of that. Your objective function is for profit. Look at the third line of that chart. Profit per ski. What would be our profit function? $70X plus 50Y is our profit. $70 per downhill ski, $50 per cross country ski. Add those together, that's going to get our profit. That's what we're trying to maximize. So that's how you can build your inequalities and your objective function. So 19 sets up that chart. I really like setting up that chart for a lot of the word problems. I think it makes it easier, makes it make sense where you're getting things from. So don't shy away from doing a little extra work and writing a chart out. Some of you can do it without it, but I think it does help some. Okay, so so that's what we're working on with linear programming. It takes just practice doing these things, and I would do a few of the maximize, a few of the minimize from the 9 through 17, and then spend most of my time trying to work on the word problems there because they're harder. The other ones, they give everything to you. It's not, it's just a matter of can you graph them the right way. But the word problems are a little tougher. So anyway, all right. That's the last lesson of the semester. Nice and sweet and short.